Hi, everyone. Welcome back. We're going to be doing a session in here. This is being live broadcast and also podcasted. We're live right now on the ONIG website, LinkedIn, Twitter, Facebook, and I think also Periscope. I believe is Periscope. I'm not quite sure on that one. Not Periscope. Okay. So anyway, but for everyone that's plugged in externally as well, welcome. So this is, I think, one of the most fascinating topics I think we're going to be covering here at the AI Networking Summit. It talks about democratizing AI through next generation networking. So what is the real big role of networking within AI infrastructure? And especially we're going to be talking about GPU clusters and that design pattern that's been in the marketplace for a while. So for those who didn't read the session, I'm not going to go into it in a lot of detail, but I think the last sentence kind of says it all. The discussion will delve into the transformative potential of AI and networking, the role of open standards, and the democratization of AI through scalable high-performance networking solutions. So I think that's the context that we wanted to provide. Song Wang, who is from ByteDance, wasn't able to make it at the last moment, but we are going to talk about ByteDance's deployment. Anyway, just wanted to give everybody an update on that. But we are joined with Hasan from Broadcom and also Darrin from Arista. I am Nick Lippis. So I'm going to ask Darrin and also Hasan to give a little bit of background on their career. So Hasan, you want to start?
Sure. Thank you, Nick. Name is Hasan Siraj, work for Broadcom. I've been there 5 years. Before that, I had 18 years at Cisco. At Broadcom, I'm focused on product management on the silicon side of the house, where I manage the software products, the software ecosystem, and some of the next generation AI networking products that we're building.
Okay. Darrin, go ahead.
Okay. I'm Darrin Thomason. I'm one of the VPs in customer engineering organization at Arista. So I have responsibility largely for the field engagements with our customers, building everything from enterprise networks to large-scale AI networks. I have a lot of other duties at Arista, and including some of the campus elements. But I've been at Arista almost 12 years, so it's been an amazing journey for us, and we're excited to be here today.
Awesome. Great. Great. Thanks. And welcome, guys. So we're going to first start off with the role of networking. Okay. What is the role of networking and infrastructure for LLMs and GAI deployments? So let's try to get a level set, right there. So I'm going to first, Darrin, if you can kind of take that, Arista has been, in a lot of these big deployments, and then Hasan will go to you. But actually, I just realized I wanted to talk a little bit about ByteDance first, and their deployment. So they have a 10,000 node GPU cluster. Is that mostly an Ethernet, fabric in their GPU cluster? So Hasan,
yeah. Unfortunately, like you said, Song could not be here, but Ethernet is kind of right now the de facto standard as far as hyperscalers are concerned. I would say 6 of the 7 hyperscalers are using Ethernet for their large cluster deployments. I will let you guess which one is not using it right now. But ByteDance, and they have a very nice paper out, right? It's with Peking University that gets into the detail. But the gist of it is they're using something from our side, which is called the Tomahawk 4 technology. This is a 25.6 terabit switch ASIC. And they have a 10,000 node cluster, just like Nick said. It's a 3-tier design. And they use something what we call a rail-based architecture. Right? There are 2 popular designs when you're designing these AI clusters. There is rail-based design, and then there is this fat tree topology, or you can call it the leaf spine topology. And fat tree is interesting. This is where when you're connecting servers to top of rack, there are usually 8 GPUs in a server, and you will connect them to a different top of rack. And this is to reduce the amount of latency, right, for different loads that are out there. They are also focused on solving 2 problems that we'll probably discuss down the road. One is how do you solve the load balancing issue. In this particular, they use ECMP, but then they're also using very specific techniques on top of it. Congestion management is a key problem that they've tried to address. Some of you may be familiar with this technology called DCQCN, right? That is kind of the default congestion management technique that's out there. But it has its limitations. And ByteDance, what they have done is they have made enhancements to solve this problem. And this is one area that is an extremely important area which requires standardization. Like ByteDance has solved it in one way. You may have heard of something called SRD that Amazon is using. Google has something called Falcon. Alibaba talks about HPC C++. So this requires standardization, but they have solved this problem and built this 10,000 node cluster. It's Ethernet based, it works. And while we talk about it, right, this is our previous generation of technology. They are already on to the next generation that we're talking about. But besides this, there are other hyperscalers who have publicly talked about their AI cluster deployments. Oracle, OCI, talk about a 30,000 or 32,000 node cluster that's out there. Amazon at reInvent talked about a 64,000 node cluster, right? That is Ethernet based. Alibaba, right? They're one of the first ones to adopt a Tomahawk 5 technology, right? So their AI deployments are based on Ethernet as well. And maybe Darrin, you can comment a little bit on Arista. Meta published a blog on how they have deployed a large cluster. Maybe you can talk a little bit.
Yeah, I think in their blog they said, listen, we're using both. We're using InfiniBand and we're using Ethernet, and they both work. They both work well. And I think obviously I think it's 24,000 GPUs is what they deployed, and it's continuing to work incredibly well as they scale out. So that's the start. Is we know that Ethernet scales incredibly well when it comes to the AI space, and Meta has publicly commented on that and what they're doing there. So I think back to your question on what's the network here to do when it comes, like, we connect things really fast, right? It's a simple problem, but it's the AI networks are slightly different. Hasan sort of hinted at this a little bit on, we have to have reliable delivery. Like if you drop a single frame in an AI network, we maybe have to go back to a checkpoint. It's like much more costly than that of the typical Ethernet data center technology. So we have to deliver very high scale, very, very wide ECMP designs. One design that we're working on today is 144-way ECMP. If you could think about just how big that is when it's all set up. So I think the role of networking in that democratization piece is that, one, Ethernet should give you choice because it's standards based, right? And then we've got to tackle all these other problems, which we're going to get into a little bit later on. It's a high speed 400 gig and soon to be 800 gig host connection. We're talking lots of host connections, possibly 8 out of an individual DGX or individual device. You're scaling the spine, as I said, in hundreds of nodes, and then you got super spines. It's crazy. And then I think we'll also talk about some of the optics side of things as we get down that path. But really, the role of networking in AI is deliver a fast, reliable network that's as low a latency as possible. But I don't think that latency is the only game in this space. So you may have a different approach.
No, I think that was very well put. What I would add to this is, when these clouds were built and what the enterprises have been dealing with is solving a virtualization problem for the last 15 years or so, right? This is where you have compute and you're trying to run multiple workloads on that piece of compute. With LLMs, we are now faced with a distributed computing problem, right? Because if you look at GPT-4, which is 1.2 trillion parameters and maybe trillions of tokens, this model is not going to fit on a few cores of a CPU or thousands of cores of a GPU. It requires hundreds and thousands of GPUs. So when you have hundreds and thousands of GPUs and they need to act as one entity, what do you need? You need a strong, resilient network. Right? And this is why networking plays an extremely important role in your AI deployments. Meta actually has also published and shared this at one of the forums where they talk about the recommendation models. And if you are using Facebook or you're using any of their social media apps, Facebook specifically, right, they're looking at your activity and then they're making recommendations on what kind of ads you're going to get. And they ran, and they have a lot of recommendation models, and they ran multiple recommendations models. And they found that up to 57% of the time was being spent in networking, right, when they were doing this training. And when you are spending millions, and in their cases, billions or tens of billions dollars in training, your most important asset is the GPU. You want to make sure it is utilized, it is freed up for others most of the time. But if that's not happening, right, it's a problem. And network is the one entity, right, that has to address that issue.
Like Ken Duda, one of our founders, says, when the network ain't working, ain't nobody working, right? And it's that times so much more. When you're spending, as you said, billions of dollars on GPUs, you want to make sure you're running those 24/7, 100%. Like if your network is problematic or you're having any type of issues in the network, it's money. So
Okay, great. So we got big scale for sure, and even bigger scale than that, because we know that even though the Azure deployment isn't on Ethernet, but they will be kind of transitioning, but it's InfiniBand. They're planning about 1 million, node cluster. So that's kind of like the scale that we're talking about, here, and we're just at the beginning, but those are mostly for training. So we'll talk about inference in a little bit. So there is kind of the back end and the front end of these clusters. The back end is really kind of what we were focusing on more, and that's where the GPUs, connect together. And then there's the front end, and I kind of think of the front end as that's where, either we're extending a data center out or we're connecting into other hosts, right? So, and there are requirements for both ends of this on the networking side of it, but I think we're going to spend a little bit more time on the fabric piece of that, and then we'll get to the front end in a second. So then, as we've been talking about scale, let's talk about the challenges that is now being placed upon kind of network infrastructure. So there's a couple of key things here, and so there's power, there's optics, there's the multiple as the clusters grow. Like we've been deploying within large campuses and hyperscales as well, like a 2-tier kind of leaf spine. We're now adding more tiers to that, which is a little bit kind of confusing, to wrap your mind around. Load balancing issues, congestion control issues for sure, failover, issues, job completion times, oversubscription. There's just a lot of. There's also synchronization. There's calculation. That's going on in the network as well. So, I guess as we think about challenges on scale, which ones are the most pressing challenges, and which ones are we clear on where we have solutions towards?
That list you just gave, if you think that networking's easy, just think about all of those things that we have to overcome. Obviously, right now we're seeing a tremendous challenge around power. That seems, because a lot of these data centers just aren't built out to handle the massive amount of power that these large GPU farms are needing. So there's, when you think about the network, it's maybe 10, 15% of what we're, the cost of the overall infrastructure. And certainly from a power standpoint, it's just off the charts, right? So I had a customer the other day, they said, we have our typical data center, and I walked in and there's one DGX node in the rack. And they said that's all they can put in that rack because that's all the power they have for that rack. Right. Wow. And so now when you're starting to think about people are loading up entire racks of these large scale GPU clusters, the power is a huge thing. And then you have the switch power, you have the power of the optics. So I think power for us is one of the big things in terms of a limiting factor right now. Mm-hmm. People are building new data centers that are bringing in large amounts of power. They're not building data centers in countries. Unfortunately, in Europe, there are some countries where power is hard to get at this point in time due to some of the conflicts over there. So we see a lot of that, and we're now being asked to architect around that. That's one of them. You You want to pick one or the other on the list of 30?
I mean, I think, Nick, you summarized this list very well. And I mean, in order to understand, I think it's important to understand how machine learning works at a 10,000 foot level, right? There are 2 or 3 things that happen. You do a lot of computation, right? That's compute. I hated matrix multiplication, but that's what's happening, right? When I was college. So when you've done all these matrix multiplications, you have a bunch of results, right? You have these weights, gradients that come in, and all of these GPUs are communicating these with each other, right? And once you're done, you synchronize, and then you iterate, right? You repeat this process over and over till you come to some kind of error level that you are comfortable with. So if we look at this process, there are a few things that are happening, right? One thing that's very different in this case is you have flows, what we call elephant flows, right? If you look at the regular internet traffic or even your own data centers, you will have hundreds of thousands of flows, and they load balance very well because there is a lot of entropy, right, when you have this number of flows.
There's a lot of what?
Entropy, right?
Entropy.
Which means
Okay.
We spray well. We
Yeah.
can spray the traffic.
They
across
balance
lots
well.
of them, yeah. So
and in the case of elephant flows, you will have a few flows, and if you don't load balance them right, you can have a lot of congestion. Another important element is when these GPUs are communicating with each other, you can fill up the links very, very quickly, right? So this is where congestion management, like you pointed out, is an extremely important phenomena that needs to be dealt with. One specific problem in this is what we call incast, right? Where one GPU is getting traffic from 5 or 6 other GPUs and it's overwhelmed. How do you deal with this kind of a situation? Another thing is these jobs, even you have tens of thousands of GPUs, you're talking about, GPT-3 on A100 took like a month to train, right? With thousands of GPUs. So how do you deal with failovers, right? If you have failovers, you're always going to checkpoint to the last state that you maintain. So in order to get job completion time, which is the most important metric, you want to be able to deal with these failovers extremely well. And the last thing I'll say is, and Darrin alluded to this, he talked about latency, and that's an important factor, but not latency through a switch. What's important in this case is something that we call tail latency. Right? This is where, when do you receive the last message? Because only when you receive the last message, you can start the next iteration of the machine learning cycle, right? So, and that is where congestion, again, plays an extremely important role. So all of these things, right, are what make AI workloads different from what enterprises and clouds have been used to over the last 15, 20 years. And this is why you need to think about different ways to solve this problem.
That was actually, I found that fascinating. So like really we're measuring latency almost like as the last packet leaves. So it's the whole train, of packets, because like you can't kind of, I guess, go through the next, whether it's token processing or whatever the GPU needs to process until that last packet kind of comes through. That's, yeah.
I mean, it's amazing to me how much time we spend on the load balancing side of things, right? So it's, as Hasan said, the sheer elephant flows, and then there may not be a lot of those flows. You're talking flows that are 100, 200, 300, 400 gig in an individual flow. And so how do I move that around very easily? And so I think there's a lot of innovation going into that space right now. We'll talk a little bit later about some of the Ultra Ethernet stuff, but I think this is the network itself has lots of links, and then I have to figure out how to push the traffic across all of those links in an efficient way, and then that gets into the overall quality of it too. So we talked a little bit about, if you think about this, even if you're building a 2-tier or a 3-tier network, right? Because to get to 1 million plus node, like it may be more than 3 tiers in some cases to get that. I know we can build a fairly sizable 2-tier network. We can build really large 3-tier networks, and now you got to start worrying about things like, how much, what optics am I using? Am I using copper cables to my top rack switches? Am I doing end of row? So all of these types of challenges are perhaps different than what we would deal with in the typical data center for the back end, right?
And on just to add on to what Darren was talking about in terms of tiers, because Nick mentioned this as well. I think this is where, at one point of time, we were just thinking, look, how much bandwidth do we need, right? And now with AI, it's like it's just not going to be enough as much as we can give. So, I mean, we just introduced a 51 terabit chip, right? This is a SoC. This is one single chip that can give you 51.2, 512 ports of 100 gig, right, in a single chip. But even this is not going to be enough, right? And you're looking at 100 terabits and 200 terabits. But the one thing that you need to understand is that, and then we believe at Broadcom we are a generation ahead, but we are very excited that the rest of the ecosystem, right, is also innovating in this space and catching up. Because the difference between a 51.6 terabit chip and a 25.6 terabit chip is you'll need 6 25.6 terabit chips or systems to build an equivalent 51.6 terabit chip, right? So this bandwidth and density, it actually reduces the number of tiers that you need to have in the network, right? Which means that you're also taking up less space, that you're taking up less power, that you're taking up less cooling. And these are going to be like power, like Darren and Nick talked about it, right? Huge factor. So these are the ways that we have to think about there are, power, there are direct ways to think about, but this is indirectly how we are also making sure that we are reducing this complexity and also reducing the power footprint.
So for a 24-port 800 gig switch, when does the kind of the chipset for that start to come out?
It's there today.
It's there today.
It's much more than 24 ports.
Yeah.
So I mean, we're at 64 by 800 today, right? 1.6 is 18 months or so, probably 18 months to 2 years off. I mean, and it's, we're right on kind of that Moore's law. Every 18 to 24 months, we've seen that density double. So, like, to Hasan's point, it's like, how much bandwidth do you need? And the response is, how much bandwidth can I get?
Yeah, that's
right. We'll take everything that we can get. Today, the predominant connect is 400 gig from the GPUs, in by 400 gig, usually 8 by 400 gig, depending upon the vendor you're using. That will switch quickly to the 800 gig here, probably in the next 6 to 12 months. So, and then imagine that out over 1 million ports, because it starts to get pretty hairy.
Yeah, this is like size. It's been a while since I've done kind of product testing in the switch marketplace. That was really when we were just getting 100 gig switches, out into the marketplace.
You need to be able to afford the GPUs for that.
Yeah. Okay, so we started to touch on some of the challenges, but we can kind of drown ourselves in challenges, and so let's shift a little bit towards maybe the cost, and the biggest cost. And we've been alluding to that before, as well. We know power is a large cost component around AI infrastructure. The optics as well. So why don't we talk a little bit about cost of these systems, and then what is being done maybe to bring costs down. So there's to me, democratization does offer options and choices, and what Ethernet should promise us is a larger ecosystem participating in this marketplace to drive pricing down and drive costs down.
Yeah, I mean, I think the whole idea of Ethernet is standards based, right? So if you talk about democratization of these systems, it's about giving you choice. We've spent I've been at Arista 12 years. We've spent the last 12 years trying to give customers choice to make the best decisions based upon the product, right? So a vertically integrated AI system is usually not what the customers want at the end of the day. They want to be able to choose, hey, I want to choose my GPU, I want to choose my network, I want to choose my NIC, I want to choose which optics I want to have for this. And so I think that's really, when we look at it, democratizing AI is about giving the customers the ultimate choice. You decide what works well for you. Now, on the optics front, I think this is an interesting area because, if you're using optical interconnects between the switches, that is the most costly in terms of it costs the most of all of the power side of things from the overall dollar side of things. There's enhancements. To put it in perspective, the optics in an AI network could be 50 to 60% of the cost of an AI network. So if you don't think that optics matter, it's half or more of the price that you're paying of the network, right? And so I think that's the fundamental thing that we're looking at. Now there's linear drive optics or LPO optics, which now are able to reduce the amount of power that we're consuming by using copper cables. We're getting more efficient with the OSFP form factors. So there's a lot of work going into optimizing the optics side of this, both from a power standpoint to drive down the power, and from a cost standpoint when it's 50% of your overall network cost.
So just a few things to add, right? And I think Darrin alluded to this. From a cost perspective, if you look at this overall deployment, networking is going to be probably 10% of the overall cost of this cluster, right? It is not the most, valuable asset in this cluster, but it gets in the way of the most vital optimizations like we talked about. So it plays a very significant role. So we believe we can improve the job completion time by about 10%. So the network essentially pays for itself with some of the solutions that we have in partnership with Arista. Now, optics, I think Darrin made some very good points. One thing that we have made significant investments in, and that's very key, is you may or may not be familiar with this concept of SerDes. Like SerDes is a technology that is used. These are physical lanes that are, when you're connecting a links, right, a switch and a NIC. So the SerDes that we build at Broadcom, we believe it is the best SerDes out there. And IEEE asks for a 2-meter reach from these SerDes, and we can achieve about 4-meter reach. So the reason we did this is because if you are trying to build these clusters now with 4-meter cables, you can actually use copper within the rack and even across the racks. So essentially, not only you're reducing the amount of power that you're consuming, but you're also significantly reducing the cost because you don't have to use these expensive optical interconnects, at least between the server and the top of rack, right? So that's one area that's out there. And then linear optics, right? I think Arista is leading the way. We are behind this as well. And the reason linear optics are exciting, linear drive optics are exciting is because the reason you consume less power is because you don't have DSPs, right? You've removed the DSPs, so there's less cost, there is less power. And all results are also pointing that they are basically less prone to failure, right? And lastly, one other investment that you will see, and we are making a significant investment in this space, is called co-package optics. Now, co-package optics really means, so imagine the world moves to 100 terabits and 200 terabits, and you have 1,000 ports sticking out. Imagine the amount of power, the thermals that are required. It's not going to be sustainable. With co-package optics, we are basically packaging the optics with the network silicon itself, right? So you don't have to buy optics separately, and this is where we believe we can drive the power down by about 50%, right? Using this kind of technology.
Okay, awesome, great. Thank you both. So we have some solutions. Go ahead, Darrin, do you have?
Well, so I say one other thing point? Just to remember, like 2-tier uses X number of optics, 3 tiers, you're interconnecting that second tier to the third tier with more optics, right? So it's you got to consider that in the equation. So the most efficient network we can build would be ideally a 2-tier network. But if you have to go to 3 tiers to scale, then you got to deal with yet another layer of optics, another layer of cost. And so I think that's as we move forward, we will obviously want to scale this out as wide as we possibly can with a 2-tier network. And the majority of the networks can still be built out with a 2-tier network and to 30,000+ GPUs in a 2-tier network.
Okay. By the way, questions. If anybody has questions, feel free to interrupt and ask. Okay. So just want to make sure you all have that permission to do that. Okay. Okay. So as we scale, what breaks? Where's the bottlenecks? I know PCI, bus was one. I think we have a solution for that. Congestion control is another one. RDMA, is another one. So maybe like where in the scale do we start to see things break? And then we'll talk about how that's being overcome.
So if you're talking about scale, I think it's been now proven, right, that these 32,000 node clusters and even 64,000 node clusters can be built with Ethernet, right, and very robust infrastructure. But as we move forward, we are talking about 500,000, a million node clusters. And when we go there, you're thinking about these clusters residing across data centers, right? Because you just won't have enough space and power to put enough GPUs in a single data center. So you're actually spanning across data centers. So what you really have to think about is, how do you move this traffic across data centers, which are kilometers apart, without compromising, right, the things that we talked about, the load balancing, right, the congestion control, right? How do you manage all of this? The other important thing in this case is, when you're looking at these transfers, the main protocol that we're talking about is RDMA, or with Ethernet, it is RoCE, which is RDMA over Converged Ethernet. Now, this is a 20-year-old protocol. We've made it work, right, for this scale, but moving forward, it has limitations. And those limitations have to be addressed, right, in order to get this kind of scale. The third thing I will emphasize once again is power, power, power. We've talked a lot about this, but I mean, GPT-3, when you are trying to train this, for the first initial numbers were about 1,300 megawatts or hours of power. This is about 1,500 households, right, in the US. There is talk about 20% of the world's energy is going to be consumed by these data centers by 2030, right? If you look at from a micro perspective, if you look at an AI server itself, just compare with what used to be like a 2 ports of 25 gig or 2 ports of 50 gig AI server. It will have some storage, it will have PCI, it will have a CPU, but an AI server is 8 GPUs, which are all consuming 700 watts each. Tied to it is a NIC, like Darrin talked about today, it is at 400 gig, it's going to be at 800 gig in 12 months, right? And plus, you are also connecting the same server to the back end, to the front end, to storage. So it's a beast in itself, right? So I think you need a lot of focus on that front. I say this, we have been asked, like, hey, focus on your miracle to solve this problem. There are others who have to do their own miracles to make this happen for millions.
Okay, so what happens to RDMA and what happens to RoCE? Do they go away?
No. So I think what needs to happen with RDMA, it needs to be modernized, right? There are a few limitations that are there. The first of all, it's not built for multipathing, right? Mm-hmm. So you have to introduce that capability in there. It works with something called go back N, right? You drop a packet. Let's say you drop the 5th packet. Now you're transmitting everything that went before this. So you have to move to a model which is selective retransmits. You only transmit what you dropped, right? Yeah. Makes logical sense. And you need to be able to do out-of-order placement, right? Because RDMA expects in-order delivery, right? So we need mechanisms in place, standard mechanisms in place. And I think there are forums that we'll talk about which are trying to address, right? What do you do with RoCE? And I think there is pretty much consensus out in the industry that these problems need to be solved to make that happen.
I mean, the other thing that I would add on you ask what breaks, like, don't underestimate the role that software plays in all of this, right? The reality is that the software has to be reliable. The software has to give me the appropriate telemetry to know where I'm, leveraging queues, or I'm about to overrun a queue, or I'm about to drop frames. It has to let me know, the simple things like I have an optic that's degrading, and I know that in the next 2 months that optic is going to go out, so I can proactively replace it. Never mind all of the security vulnerabilities that we have to deal with in the world today. I need to be able to upgrade this thing and upgrade it in a way that doesn't cause me an outage in my network. And so I think it's like the hardware is important. It makes us go fast, but don't think for a second that we could run these networks without an incredibly resilient and robust software system that gives me the appropriate telemetry that I need to be able to troubleshoot and to make sure that my system is always up. We're working with a system right now, and we're having some some interesting, challenges on the incast side of things. And so we're able to quickly tell through some monitoring of the individual queues that the queue is filling up, and we know that where we're going to overflow that queue. And so then we can adjust the overall buffering on the switch to make sure those things don't happen. If you don't have that visibility in the software, you are blind. And it will fill the queue up, it will overflow the queue, you'll go back to your checkpoint, and you'll start over. And you want to make the HPC people mad, drop a few frames in the network and see if they notice.
Yeah.
They will notice, and they will call you, and they will blame everybody under the sun until they figure out who is actually at fault. So like the hardware is important, the software is important, and the congestion management pieces are important, and there's a lot more there that I think that we can innovate and offer.
So let's go back to hardware. Mm-hmm. That's it. Inside the silicon, so that's where we're going to have to kind of deal with congestion control. So new congestion control, new transport, as well. The UEC group has a couple of working groups working on that. I guess, Hasan, is this a 6-month, process to kind of new standards around transport and congestion management, the extending of RDMA or modifying RDMA? Is that work also happening at the UEC as well? I guess what's the timeline for, usually your standard process takes a long time, but we don't have that time, so I'm sure that's being accelerated now, and then the time to get that into the chipset.
Yeah, I mean, I think the urgency is felt by the ecosystem, right? I think we started off Broadcom and Arista were one of the 10 founders of this consortium a year ago, but now there are 55 members, right? This is one of the fastest growing consortiums out there. And like you pointed out, there are different working groups, right? How to deal with congestion control, modernize RDMA, which is the transport layer. There's also groups on software and APIs. And everybody is really working on specs. We actually have contributed a lot to these specs. Mm-hmm. And I expect that by the end of this year or even before this, we will have consensus on some of the main pieces, right? Which is this transport piece, the congestion control piece that requires standardization. And probably in 2025, you'll start seeing products come out which are UEC compliant.
2025. Okay, great.
But those products will largely be on the NIC side, right? So we don't expect a lot of changes on the switching side right now, at least some of the initial plans, right?
That is correct, right? So some of these capabilities, I mean, you have some of these capabilities in the switches itself. There is also how do these NICs works in conjunction with the switch. So a lot of this innovation that will happen is going to address that connection as well.
I mean, you have customers that are buying 400 gig, 800 gig switches today. The last thing they want to do is swap them out next year. But I think UEC is that kind of lighthouse in the future that we see. And whether it's packet spraying, whether it's as you said, the modernization of some of these 20-year-old protocols, that's going to make the big difference for us. And that gets back to you now have a standard that everybody can build to, so that we can further democratize and further give you choice in that space. Today, Rocky is largely driven by one vendor, right? And so the idea here is that this is 55 today. It'll be more in the future that can build this and continue to grow this.
Okay, actually, very good point to kind of differentiate where those standards are going to be taking place within the network, so that you don't freak out all of your customers, that you're going to swap out all those switches. Okay, great. I think we kind of hit the fabric pretty well, across all the major topics that we wanted to cover. We have 5 minutes or so. Let's switch our attention to the front end, of the network. So as we're scaling this up, 200, 400 gig, 800 gig, connecting, the front end. So, I guess what is there any special requirements that we have to be thinking about on the front end? And I think the last thing I want to try to get to is class of customers, that's consuming these kinds of systems.
I think to just level set everybody, does everybody understand that the back end network is really GPU to GPU traffic, right? So that's high speed GPU to GPU traffic. We don't usually connect servers. We don't connect storage and other devices into that. That's just GPU to GPU. The front end is where we connect all of our storage. It's where we'll do, different compute cycles. And so the front end is largely the data center networks that we're building today, right? They're just faster, So if you have a typical leaf spine data center network that's 100, 200, 400 gig, I've seen the front end connected. It's usually at whatever speeds I can get from my storage nodes, whatever speeds that I can, if I'm running 400 gig to my back end, I'm usually running 400 gig to the front end on the GPU node itself. And then storage is however fast I can get there, 100, 200. We're seeing a lot of 200 gig attached storage, and we'll see it, I'm sure, go to 400 gig as the storage gets there. And so I think that's it's what we've done well today. So all the rules still apply in terms of, do I need buffers in that space? Do I need a lossless fabric? Do I need the same visibility that I perhaps have on the front end today in my typical data center network? So the front end is important, but the back end is where we just have this massive scale at right now. So you could have 8 back end connections maybe for every one front end connection, to kind of put that in perspective.
Okay, that's helpful.
So, yeah.
Okay.
I think one perception that has been maybe being put in people's mind is, hey, the front end can be Ethernet, right? But you really need the back end to be InfiniBand. I think it's been proven that you can actually have a converged infrastructure, which is all Ethernet, right? I think it's been proven. It's been proven in some of the deployments that we talked about. And concepts such as multi-tenancy, right, which may be very, very important for some of the customers for specific use cases. Something that InfiniBand does not address or address very well. Whether you want to do it in the front end, which is happening a lot, right? You can also, even though in the back end, in a lot of cases, it may be just a private network, but if you are offering GPU as a service, for example, you can extend the same multi-tenancy capabilities to the back end as well. So really, you can, with Ethernet, build a converged infrastructure, front end, back end, connecting with storage, and there is out-of-band management as well. There is always a management network that's out there.
Okay, great. Last point is around class of customers. Clearly, hyperscale companies have been, they spent $200 billion this year, or they're spending $200 billion this year. So we know that they're building out, at scale. There's also multi-tenant, kind of deployments to large enterprise. We talked about some of the use cases around cancer research and drug discovery, self-driving cars. Tesla's huge implementation over at Tesla. There's solvent clouds. Any other use cases you all have been seeing, or customer profiles?
I think if you think about AI in general, at least what I'm seeing today are businesses that have a specific business problem that they're trying to solve, as you described. Whether that's self-driving, whether that's fraud detection, whether that's, I think Hasan talked about targeting for ads. Like, those customers have gone out and said, I can afford to spend a lot of money on this and build my own data centers to do this because it's going to return money. There was a billboard I saw on 101 traveling into headquarters the other day, and it says, AI without ROI equals DOA, right? And that's really the problem that we have right now. Is so these large companies like Meta and others are solving that particular problem. I think general enterprises are lagging a little bit, but I think they are going to start seeing that. Now, they may not build the large training clusters, but I think that we'll see them leverage these cloud offerings to do the training, and then maybe they'll bring inference inside.
Yeah.
And the inference engines or the inference clusters may be half the size of that of the training clusters, or even smaller. So we're seeing a lot of that 10,000 to 20,000 GPU clusters starting to crop up. And it's all based upon kind of that customer use case across the board. Obviously, the cloud guys have a big use case. Some cloud providers want to be multi-tenant. Some want to just have it for their own individual uses.
I think Darrin covered it very well. I think the transition we are seeing is the hyperscalers have been doing it for 2-3 years, right? They have now stable clusters. They're looking to scale. I think I call the second class of customers that are adopting are digital natives, right? We talked about some of the use cases around the self-driving and others. The GPU as a service companies, right? A lot of them are cropping up, right, all over the world. And also we think AI is going to be a national security kind of an agenda, right? So that's why sovereign clouds, there is a lot of talk about this. A lot of countries are trying to build these sovereign clouds. enterprises I agree with. But one thing the enterprises will have to decide is, look, we talked about how expensive this infrastructure is going to be, right?
Yeah.
To buy it, to operate it. So, but it can be a huge competitive differentiator, right? So this is where the decision has to be made, whether you do it yourselves, do you use something that's out there and pre-trained and then do incremental training. I mentioned this in the morning. I think a good model that I've also seen is a hybrid model, right? For these kind of customers, like a company that does a lot of auctions, right? They basically, the hybrid model, how they adopted was, look, they have a lot of data in terms of how much I can sell something for. They have this data and they have their own model for this and they can train it. But for if there's an item, to get the description of that item, right, they can use something that's available like ChatGPT and API to ChatGPT, right? So I agree with Darrin. Enterprises are lagging, but I think this is what they're striving to solve. Like, what is the big problem and what is the best approach for me to go about it?
Yeah, that all makes like so much sense. And I think there's a couple of things that go through my mind. First of all, Tesla is always a great company to kind of like look at. It's like they've invested so heavily in self-driving. They have that infrastructure. It's been put in place. They have the data. They have the training. They have the learnings going on right now. That is such a competitive differentiation across other large, corporations, whether that's GM or Ford or Fiat, BMW, Mercedes, or what have you. Those two have implementations, but from what I've seen, not nearly near the scale that Tesla has, and they don't have the data training either. So it's a major competitive differentiation. And the financial services as well. You got fraud mitigation is like one of probably the top, use case. And for those companies who maybe not are investing because of the price point for AI infrastructure, there's a major differentiation in those markets. I guess all I'm just thinking of is that it's really expensive. Hopeful that the democratization that we've been talking about and how we have more options and choices for corporations to build, that barrier of entry will become lower and more companies can invest in that infrastructure and in their business. So, but if it stays really high for a long time and only those companies that can afford to it, I think those companies actually run away with a lot of market share. Yeah. I'm sorry. Go ahead. It's here.
A quick question. So Hasan, you talked about the distributed data centers. Right? So what is the implication on the WAN side of the house?
Yeah.
No, this is exactly what I'm talking about, right? This is your data center interconnect, you can call this, right? Because this is one supercomputer that is spanning across data centers. And when you're talking about this interconnect, this is very large bandwidth because a lot of traffic is going across this, but it is just one cluster. So you need to make sure that, the aspects that we discuss, right? That the load balancing is not compromised when you're doing this, right? The congestion controls are in place. And that is a problem that needs to be solved, right? When you get to these 500,000 or million node clusters.
Yeah. Okay. Awesome. Sanad.
Question. Sorry. So you talked about what's happening in the Ultra Ethernet Consortium and ROCm version 2. So and I haven't looked at the forum, so I don't know. But outside of solving problem at the fabric level, and so if you put that aside, can we even solve that problem if we don't tackle what, for example, NVIDIA, what the job placement, so what would management and control plane protocol be for job placement across GPUs? So replicate something that Nickel and like Bluefield come together in a solution. So if you look at when NVIDIA, places the jobs and when they create their rails, it's from GPU to GPU, and then it calculates real-time, whatever performance and things like this. And then as they place those jobs, they're in position to place the jobs, right? It's really performance from GPU to GPU across all these rails that are available from GPU's perspective. So can we even solve that problem from the Ethernet fabric perspective if we don't have an insight to control where workloads are, where the jobs are placed?
Great question. Yeah.
I guess the one way to think of it is if we can give you an any-to-any, non-oversubscribed path, that sort of takes care of what the network can do. Listen, I can't make a 400 gig port go faster than 400 gig, right? So the reality is, or an 800 gig port go faster than 800 gig. So I think job placement matters, I'm not arguing that, but there are always going to be, like, our focus has been make the network the most efficient that it can possibly be, meaning we have the lowest possible latency, we have the ability to load balance and handle a large ingest of traffic, and make it highly resilient to handle that. Where you place the jobs on top of that, I mean, I can't fix it if they decide to put 8 jobs on this GPU over here that is oversubscribed then because I've got too much oversubscription from a GPU standpoint. That part is going to have to be really in the job scheduler side. But Nickel and some of those things are getting better at that, and integrating that. Our focus on the network is to do what we can do, right? I don't know if you got any other insights.
Yeah, I mean, I think on top of this, the forum, if you look at this, there is one aspect that's under discussion, which is called in-network computing, right? And this is where, depending on how the jobs are placed, this is where the fabric gets involved as well, and some of the processing can happen, right, on the fabric itself. I think this is also something that we have to see how it works, but there is definitely, theoretically, there is value on doing this, and this is something that we are actively engaged on.
Okay. We are past time. I thought we were actually end early. We actually went 5 minutes over. So everyone, thank you so much for hanging in there, and being a great audience. Darrin and also Hasan, thank you very much for all your insights and sharing during the session. And so this has been the Built for Trust podcast over at the AI Networking Summit. Thank you, everyone.
Thank you.
Thank you.